Hi guys, welcome to lecture number 9 of our PyTorch series. So guys, essentially we have been doing this deep learning project where initially in the first lecture I showed you how to complete the EDA. Then in the second lecture I showed you how we ended up training an LSTM. And now in the third and probably one of the final lectures for this context of discussion that we are having, so I'll explain you how to improve the system. So guys, a lot of people can maybe go on to level 1 and level 2, but we should always understand how to improve the system. And this type of skill is very important, guys. So I'll tell you, I'll spend 1 minute in just explaining why is this important. So understand, guys, AI tools are great at, let's say, generating code, right? But sometimes you will find out that they have really written a lot of code which is very verbose. So the sense is that it's not actually needed. A lot of things are not actually needed and can be simplified as well. So like obviously in the next iteration of a call you can just ask the LLM that, hey, can you just simplify the code? So that portion is okay, but just try to understand that AI is going to essentially generate a lot of code for you. And programming, not only programming, or all skills essentially would become little abstract. That means earlier that the amount of effort required to, let's say, do something will not be same. It would be very less effort would be required to do a lot of stuff. But then if you have the knowledge on how to improve the system, right, you can really leverage AI tools and this type of knowledge, and you can go by that process and really get a lot of stuff done. So that was the intention behind this lecture, and now I'll be explaining you that what we are doing. So essentially, guys, first of all, I'm reading the process file. I think all of you know this thing that I've been creating a process file, which is a good habit of just having another file for all your data science workloads, and that is fine. So all of you know that this is the same set of action that we have done. That, hey, what is the problem statement is that based on 24 hours of previous data, can I predict can I predict the next day power consumption? So that is the problem statement in hand. Okay, and we are training an LSTM for that. So let me just walk you through that portion of the code once again, line by line, so that everything is clear on the facts. So guys, essentially what we are doing is that we are importing all the necessary PyTorch modules. Then we are just using the device that is available. So guys, on the device part, I have told you about GPU, and in my YouTube channel a lot of lectures would come on GPU. Just a quick revision that, hey, we use GPU essentially for training neural nets. And the best part is that the calculation specifically in terms of matrix multiplication is very fast. And the fact is that NVIDIA is the market leader in this space. They first created GPUs in order to just maybe have video games, but who knows that the entire world is now training neural networks on GPU, and it is a very essential component, guys. Having good knowledge of GPUs is very important and a must-have skill for future AI developers. So I'll be keeping you updated on the lectures when it comes to GPUs as well. Everything will come over here only. Now guys, I've shown you that why we need to do -1 and 1 dot view, so that we just have one value and the shapes and everything match, so that we don't have an error. Usually we do these type of things in sklearn also. So guys, we are just moving our X train and Y train to the GPU. And guys, simply guys, see how simple it is to use PyTorch and define a LSTM and an output layer. So we are using uh, two layers, and the hidden size is 64. That means essentially we are having two layers of two hidden layers, and each layer we have about 64 neurons. Sorry guys. So essentially we are good on that part. Now guys, the change that I have done, see, I have done no change in the code. I have only done two changes. One is that I have added L2 regularization, and I have reduced the number of epochs. That's it guys. From lecture 2 to lecture 3, this is the only change that I have done. no other change is being done, and you would realize that see, everything is same. We were doing mini batch training and everything, it's same as lecture 2, nothing has changed. Only thing has changed that I've passed the parameter to show you guys L2 regularization, and we'll talk about that in depth as well today. That's the objective of today's lecture. But before that, let me just show you the performance of the neural net on what kind of a performance the system has achieved. So see guys, now you're able to see that we have reduced the number of epochs and the loss is constantly decreasing, it's not going up. Okay, earlier if you would see in the previous lecture, if you would have watched the previous lecture fully, I'll show you that chart as well. So that model, when I ran it completely, I'm not sure how many epochs I ran in the video, but in my personal development time when I was running it, you're able to see that after certain number of epochs, the model started to uh, overfit. That means my validation accuracy is decreasing constantly, but my training accuracy is decreasing very sharply. But my model is overfitting, and you are able to see that this was going up. But now by reducing the number of epochs and adding L2 regularization, you are able to see that how smoothly everything is happened. Now you're able to see this. Only change which I did in the code is, you were able to see I added L2 regularization and I reduced the number of epochs. So guys, see how many epochs you need to train the neural net, that's very subjective. There is no fixed answer for it. There is some sort of analysis or some papers which suggest that like they have done some sort of analysis, so you can refer them, but for the time being just think of it as an experimental thing. So like, because I was able to see that in the previous iteration, about when I crossed 30 iterations, my testing accuracy was going down and my training accuracy was going up. So this is a perfect case of overfitting. Okay, what happens in an overfit model is that over time your training accuracy, let's say this is the loss. So if you will find out, this is one loss and this is another loss. Now this is your training loss. Okay, as you increase the number of epochs, your training loss was getting decreased, which was shown in the chart as well, but your test loss was going up. So that essentially means that we are overfitting. Now guys, what we have done is we have reduced the number of epochs. So guys, see, sometimes you need to reduce the number of epochs as well, since see guys, this is dummy data set. Okay, on top of that we don't have a lot of data set, right? This is about, I think, I'm not sure how many rows it was, but let me just check that how many rows essentially we have. So let's just go up and see. So training set size, yeah guys, we only have 27,000 records. So guys, always remember guys, this is a very important lecture as well, that sometimes guys, neural networks require more data. Okay, and they are like, to train a neural net you require a lot of data, and that is a lot of data, as well as guys lot of infrastructure. So on infrastructure side, specifically for simpler use cases guys, I'm talking about simple use cases, not any LLM or any foundational model in general cases. But guys, organizations don't have a lot of data, neither they have a lot of infrastructure. So that is why sometimes in traditional organizations, or any most of the organizations, specifically if you'll be working in corporate industry, they'll be using ML based approaches, not DL based approaches, because guys, the volume of data is low and the training infrastructure is also very limited. But sometimes DL based approaches also come, and guys, now as I said that now we mostly consume a lot of LLM, so most of the workloads are like taken care by LLM. In case we have some regression based modeling, then only I think companies should be using ML based approaches. I think otherwise, if you like design the architecture well, you could crack almost every problem with the current set of LLMs, and they're going to keep getting better. But now guys, let's come to the lecture, that is, how is L2 regularization helping us? Okay, this is an important part. How is L2 regularization helping us? So guys, not sure how much depth needs to be covered on this aspect, but let's just start from the top and go to the bottom of the pyramid. Let's see what is regularization. Essentially, it is a technique that helps my weights converge better. Okay, converge better. That means, in simple terms, that if I'll be using L2 regularization, there is a good possibility that I'll find optimal weights. Okay, that means my weights, like my loss function, would converge in a better manner. Now, this is the bare minimum knowledge which all of you should have. Now, like, this was level 1 level of understanding which you should have. Okay, now L2, or okay, this L2 is level 2, not this L2. Now the thing is that L2 level is just like level 2 level of understanding, which just shows you that what exactly happens in there is that your weights, okay, weights don't explode. So if you are using L2 regularization, and guys, see in PyTorch we are using L2 regularization with Atom Optimizer, and it is just like one line of code. You are able to see it. Just you have to pass one parameter. So as I said, guys, coding wise it might not be very difficult, and slowly you would become better coders anyhow, guys. And mostly, as I said, that a lot of workloads would be driven by AI produced programming, so that's okay. But guys, you're able to see that your weights don't explode. That means sometimes what happens is, guys, you say, let's say you have a w1 is 10 and w2 is 0. So guys, here you are able to see that magnitude of your weights is very different. So in this kind of scenario, usually your weights don't your weights don't converge, and your loss, it's not like weights don't converge. I think this is wrong. Let's just remove this. Essentially we should write loss converges better. And if your weights are essentially like there's a large difference in their magnitudes, your loss function doesn't converge well. Okay, so this is very important, guys. Okay, that you need to understand that what is the essential problem statement, that we need to make sure that, let's say, this is the loss and this is the value of weight. So for what value of weight my loss would go down, right? So might be this might be the optimal value. But if your weights are like very up and low, that means they have a lot of variance in between them. That's why, guys, if you'd seen in this project, we have used standard scaling, right? So we have used the min max scaler, wherein we are doing x minus x min and x max minus x min, right? So in a lot of neural network based approaches and in projects, you would find this type of transformation as well. So guys, all these things happen, and they happen in industry as well as everywhere, so that your weights don't are not too up and down, and hence your loss function converges better. Now that's part 2 of the game. Now guys, understanding level 3 is very optional. If you want to understand that what exactly happens in L2 regularization, you can continue, and please subscribe to my YouTube channel as well. But if you don't want to, you can skip it probably. But like, I want to explain you, if you like neural networks and math, so you can stay back. So guys, see what happens in L2 regularization is that initially your weight update formula is this. I don't know how many times I have written this equation in my YouTube channel, but yeah, this is one of the very important equation, that is, this is how your weight updates usually happen. Okay, now the thing is, guys, what happens when it comes to L2 regularization is that your loss function is L old minus lambda, and it's wi square. Okay, this is just a way of writing things. Your L old is nothing but the loss function that we are using. So in this case we are using MSC, and guys, this is nothing. Okay, this is just lambda is nothing, this is a hyperparameter. And guys, don't confuse this lambda with this eta. This is your learning rate. Okay, this is your learning rate, and this is your hyperparameter. And guys, this is nothing but this is just summation wi square. Okay, so you have weights and you're just summing over it. Now guys, usually this is the equation, and Li is equal to L old for normal loss functions. But for L2 regularization, this is the equation that you need to know. Okay, so guys, let's just try to take its partial derivative with respect to wi. What will happen? So you will find out what is going to happen is that we will have this something like this. Okay, and we'll have this 2 will come over here. So guys, if you know a bit of partial derivatives, you will understand this. This is simple derivative which we have taken. Okay, now guys, what we'll do is we'll substitute this. So let's just mark this as equation number 2, and let's mark this as equation number 1. So guys, if you will put 2 in 1, what will happen is, let's just see, you will have wi and you will have wi minus your eta, and then this thing would become rate, like the old weight, its derivative with the wi plus 2 lambda wi. Okay, now let's do one thing guys, let's just try to multiply this thing inside as well. So what will happen over here is that you will have this thing over here. So guys, I'm not doing anything, I'm just multiplying this thing. So yeah, this would be something like this, right? And then let's just do one more step. Let's just take wi common and let's just write it as this minus this old and something like this. Yeah, so guys, see, just understand what is happening. This is known as decay parameter. So some people or researchers, what they do is they call L2 regularization as uh, ridge regression as well, which is just like, it's okay, as I shown you, right, how you can just make it in the form of regression, but it's more than that. It's not necessarily regression, it's a regularization technique. So see guys, here, because of this decay parameters, your weights don't become too high or too low, and neither you would find out that it would ever become zero as well. Okay, your weights will not become zero, because if you will see this term is very important guys. This term is very important. This term is 1 minus 2 lambda and this thing. So guys, you know guys, right, mostly your lambda and learning rate are often like less than 1, and if you multiply any number like less than 1 in that sense, this will always be less than 1. So you'll always have some sort of value coming in, so it won't let this entire thing vanish and converge to 0 as well. So in simple terms guys, it, because of this decay factor, right, which I was able to just to get it to with some basic maths, this decay parameter, it was not able to because of this guys, your weights don't go up and down. That means they don't form into extreme conditions, and because of this, you would often find out there that your neural network would converge better. Okay, so guys, this was from the mathematical standpoint. I explained you in three levels of details. You can just pick that whatever uh, level is required for you. If you want to, like, if you are like into research and all, then maybe what you could do is you could take the Adam equation. Okay, so equation of Adam optimizer, and just try to do the maths with that kind of L2 regularization. So if you have time, you can do it. But like, yeah, that's only for research people. Other folks can skip it. And guys, see, the main objective of this lecture was just to give you an update that hey, you can improve on systems like the way I did, and all you need to do by coding wise is just guys apply this weight decay parameter. That's it guys. Okay, so a lot of people could ask that hey, what is this weight decay parameter? So I've shown you, like I've shown you in maths as well, that what is that weight decay parameter. So I mean, you don't need this granular level of information, but sometimes it's good to have this amount of information as well. This would help you just train better neural networks and help you formalize and conceptualize better. So guys, on that note, I would like to end today's lecture, and guys, please subscribe to my YouTube channel and have a great day ahead. Thanks.